In this video, we're going to take a look at rational functions. Now, when we say a rational function, we mean a function that can be written as the quotient of two polynomials. So if f of x and g of x are polynomials, then r of x, which is equal to f divided by g, is a rational function. Now, there's a lot of interesting things about rational functions. One is that the graph of a rational function may have asymptotes. Asymptotes are lines that a function can approach. Let's take a look at our two toolkit functions that we've seen. F of x is equal to 1 over x, and f of x is equal to 1 over x squared. Both of these are rational functions because 1 is a polynomial and x is a polynomial. X squared is also a polynomial. So let's take a look at these two functions on a graph. Now, we've seen these graphs in an earlier video, but it's useful to revisit them. Here's the graph of f of x is equal to 1 over x. Notice that it approaches the x-axis as x goes out towards infinity and as x goes out towards negative infinity. It approaches the y-axis as x gets closer to 0. But it approaches in two different directions. It approaches a y value of negative infinity as x gets closer to 0 from the left, and it approaches positive infinity. The y value approaches positive infinity as x gets closer to 0 on the right. So this has a vertical asymptote, which is the y-axis, which is just x equals 0. So it has a vertical asymptote, a line we approach, which is x equals 0. And it also has a horizontal asymptote of y equals 0. Now let's look at 1 over x squared. The graph of f of x equals 1 over x squared is both similar and different. As x grows towards infinity and as x grows towards negative infinity, the y value gets closer to 0. So once again, we have a horizontal asymptote of y equals 0. As the x value gets closer to 0, the y value shoots off towards infinity. And in this case, on both sides, it's shooting off towards positive infinity. So we have a vertical asymptote at x equals 0. Both of these had a vertical asymptote of x equals 0. Notice that when we plug in an x value of 0, we get 1 divided by 0 in both instances. So this tells me something about where the vertical asymptotes of rational functions are going to be. They're going to be at values of x where the denominator is 0 and where the numerator is not 0. So if a rational function can be written as f of x divided by g of x, a vertical asymptote will happen at x equals a when the numerator is not 0 and the denominator is 0. That is when I plug in the A. So if we're trying to check and find vertical asymptotes, basically all I need to do is find the zeros of the polynomial in my denominator, and then make sure that those zeros are not also zeros of my numerator. If they do have matching zeros, then what I would do is I'd factor out those common factors and cancel, and then rewrite the rational function and start over. As we saw, sometimes when we talk about the vertical asymptotes, we want to know the behavior of those vertical asymptotes, specifically if, as we approach a number, is the function value shooting off to positive infinity or negative infinity. And we saw that in some cases, approaching a value from the right or from the left shoots us off to different sides. One may be positive infinity and one may be negative infinity. The notation we're going to use for that is x is going to a, and then we'll write a plus sign in the position of an exponent. And that's going to mean we approach from above. In other words, we're on the right side of A on the graph. X going to A with a negative sign in the place of the exponent means that I'm approaching from below. So I'm looking at X values which are below A. So A with a positive in the place of an exponent means I approach from above, so I'm to the right of the A. A with a negative means that I approach from below, so I'm to the left of the A. Now, on the other side, when we're looking for horizontal asymptotes, what we're doing is we're seeing what happens as the X values get really, really big. If, as the X value gets really, really big, this rational expression, this rational function, gets close to a number, we'll call it B, then we'll have a horizontal asymptote of y equals B. So we're going to have to see what happens to this expression as x grows towards infinity and towards negative infinity. And the notation we'll use there is the arrow notation. As x arrow infinity, then the rational function is going towards B. Or as x arrow negative infinity, the rational function goes towards B. Let's take a look at this example. We have a rational function, which is a linear function divided by another linear function. We have x plus 6 divided by x minus 2. We're going to determine the vertical and horizontal asymptotes algebraically, and then we will graph the function and see if it matches up. All right, let's first start out by looking for the vertical asymptote or vertical asymptotes. This one has actually one vertical asymptote, and it is going to happen when the denominator is equal to 0. So the denominator we set equal to 0, and we solve for x. X equals 2 is the vertical asymptote. That's a vertical line with points whose x values are all 2. So we have a vertical asymptote at x equals 2. Now we can check that that 2 is also doesn't, let me rephrase that, also does not give a 0 for my numerator by plugging that in. Obviously, when I plug that in, I get an 8 in my numerator. I should have said that, but I saw that before I moved on. But anyways, plugging in 2 gives me a 0 in the denominator and an 8 in the numerator. So that is where I have a vertical asymptote. The vertical asymptote is the line x equals 2. Now we can also say as x goes to 2 from above, what is my function doing? Is it going to positive infinity or is it shooting off towards negative infinity? Now, the way I like to do this is I like to plug in a number that's really close to 2, but a little bit above 2. Plug in something like 2.001. If I plug in 2.001 into my function, what would I get? Would I get a very large number or would I get a very small number? If I plugged it into the numerator, I'd get 8.001. And then I would plug that into the denominator, I would get 0.001. If I take 8.001 and divide it by 0.001, I end up with something which is a positive 8,001. That means this function is getting really, really big in the positive sense if I plug in if I'm getting closer and closer to 2 from above. If I'm a little bit above 2, it's going off to a positive infinity. Hopefully that makes sense. I will do the same thing for x going to 2 from below. By the way, this is not the only way you can do this, but this is one of my favorite ways, one of the easiest ways, I think. And what I would do from going towards 2 from below is I'd plug in something that's really close to 2. Let's plug in something that's even closer to 2, in this case, 1 point, lots of nines, 9999. If I plug that into the numerator, I'd get 7.9999 in the numerator, and I'd get a negative 0.0001 in the denominator. If I take 7.9999 divided by negative 0.0001, I get negative 79,999. The key fact there is that we're getting a really large negative number, which means that my function is going towards negative infinity if we're approaching 2 from below. So that's how we deal with vertical asymptotes and the approach in both directions. Again, this is not the only way you can figure this out, but for this section, this will be an efficient way to figure this out. Plug in a number that's a little bit above the value in our in our vertical asymptote. Plug in a value that's just a little bit below the value in our vertical asymptote. Let's take a look at the horizontal asymptote this time. Now, this one's going to be a little bit trickier because we're asking what's going to happen to the output of our function As x goes off to positive infinity, and as x goes off to negative infinity. In this case, basically, as x gets really, really big, let me write this down. As x goes to positive infinity, then what is going to happen to my function? Well, my function, which we know is x plus 6 divided by x minus 2, is going to behave just like another function. And here's what we do. We say, what is the fastest growth of this polynomial? Obviously, x is growing. As x gets really, really big, x is growing, and 6 is standing still. So when x gets really, really, really big, like if x gets towards a million plus 6 is not that much different than just a million. And if we get to like 10 billion plus 6, the plus 6 doesn't account for very much. The same thing with this minus 2. The minus 2 is standing still and the x is growing. So as x gets really, really big, what my rational function does is it behaves like the leading terms. Well, the leading terms are just x and x. So my rational function behaves like x over x, which is 1. Now, that is going to be true also if x gets towards negative infinity. If x is going towards negative infinity, then the leading terms are going to determine what happens with this rational function. And therefore, this rational function goes to 1 because x over x is equal to 1. So as x goes to infinity and as x goes to negative infinity, my function goes to 1. And that means I have a horizontal asymptote of y equals 1. In other words, output is equal to 1. Output is equal to 1 as x goes to positive and negative infinity. So this rational function had one vertical asymptote at x equals 2 and had one horizontal asymptote at y equals 1. We saw as the x goes to 2 from above, the function shoots off to positive infinity. As x goes to 2 from below, the function shoots off to negative infinity. Let's graph that and confirm that that's true. Now, I've graphed that with Desmos, but you could graph it with anything you want, including your TI-84. Notice as we scroll out, this rational function horizontally is not approaching 0, but approaching 1. So we're getting y equals 1 as our horizontal asymptote. I could scroll out further and further and further, and you can see that better as you scroll out further. And with the vertical asymptote, that's going to be x is equal to 2. Let's check that out. And again, as you scroll out further and further and further, you can see that both sides approach the vertical line of x equals 2. Moreover, you can see that as x approaches 2 from the right, my function shoots up towards positive infinity. As x approaches 2 on the left, so values just under 2, then the output shoots off to negative infinity. So this example shows how to find a vertical and horizontal asymptote. Let's take a look at another example. Let's graph the following, but first let's determine the vertical and horizontal asymptotes algebraically. So we'll do the algebraic thing, and then we'll graph this rational function. If you want to try this on your own, push pause on the video. In a couple of seconds, I'll show you how it's done. Okay, I think we're set up here. So to find the vertical asymptote, I need to find where the denominator is 0. So I set 12 plus 3x equal to 0, and then I solve. I think it's pretty straightforward that we'd subtract 12 from both sides and then divide by 3. So we get x is equal to negative 4 as my vertical asymptote. That is, the line x equals negative 4 is the vertical asymptote of this rational function. And there's only one because there's only one x value that gives us 0 in the denominator. Now I should check that by plugging it in, making sure that you plug in negative 4 into your numerator. It also doesn't give you 0. In this case, that is true. Negative 4 squared would give me a positive 16 minus 3 times negative 4, that's plus 12. 16 plus 12 plus 7 is definitely not 0. So vertical asymptote at x equals negative 4. Now let's look at the behavior as we approach negative 4 from on the right-hand side and negative 4 on the left-hand side. Be careful here when you plug things in, because as I approach negative 4 on the right, that is a number that's slightly bigger than negative 4. So slightly bigger than negative 4 on the x-axis is a number like negative 3.9999. So we're adding 0.0001 essentially. And a number that's slightly below negative 4 on the x-axis is something like negative 4.0001. Okay. Again, that's how it goes. I am just going to give you the answers this time. Last time I showed you how to calculate, but when you plug in negative 3.9999, you get approximate y value of 11,666.3, which is a really big number. So that means as we're just a little bit above negative 4, then my function value is shooting off to positive infinity. If I plug in negative 4.0001, then my output is negative 11,667.0.3. By the way, this is rounded numbers. I'll just say negative 11,667.0. Notice that's a negative, really big number. So that tells me my function value is shooting off towards negative infinity in that case. So that's how we can do that. Again, these are rounded values, not exact in that sense. How about the horizontal asymptote? Well, as x goes to positive infinity, this function behavior is going to look like the fastest growth on top divided by the fastest type of growth on bottom. So I look at the term which has the fastest growth, which means the term with the highest degree. That's going to grow at a pace way faster than the other terms. So in the numerator, the x squared grows faster, a lot faster than the negative 3x and the plus 7. The x squared is kind of like a jet plane, and the negative 3x, while it's growing, it's like a person walking. So we're talking about vastly different speeds here. So the x squared is going to determine what the top does. And in the bottom, the fastest type of growth is the plus 3x term. So the f of x is going to behave kind of like x squared over 3x, which is kind of like having an x over 3. So as x goes to positive infinity, well, what's this do? It's going to grow. So this thing is also going to go to positive infinity. So that's all we're saying there. As x grows, then my f of x, my output value, is also growing towards infinity. What if I plugged in a negative infinity? Well, then I get negative a really big number divided by 3, which is still negative a really big number. So as x goes towards negative infinity, my function value also goes towards negative infinity. That means since neither side gives us a function value approaching a real number, we have no horizontal asymptote. So we have one vertical asymptote in this case and no horizontal asymptote. Both sides are going to shoot off towards either infinity or negative infinity as we do that. Let's go ahead and graph this and confirm what we already know. If I graph this rational function on Desmos, I get this. Notice that as we move out and to the right, our function just keeps growing and growing and growing. As we move to the left, our function keeps going down and down and down. But there is this place where x values are negative 4, that on the right-hand side, the function shoots off towards positive infinity, and the y value shoots off up and towards positive infinity. And when you approach from the left-hand side, the y value shoots down towards negative infinity. So in this case, we see that we have a vertical asymptote, but no horizontal asymptote. And we get this picture. Let's do one more example right now. Let's take g of x, which is equal to the polynomial x plus 6 divided by the polynomial x squared minus 3x plus 9. Let's find the vertical and horizontal asymptotes algebraically, and then we'll graph it and take a look at what it shows. If you want to try this on your own, push pause on the video and try this on your own. All right, vertical asymptote would happen when the denominator is 0. So let's set that denominator equal to 0 and solve. Well, this is a quadratic, so I would try to factor first. It turns out if you try to look for factors of positive 9 that add to a negative 3, there are none. No integer factors anyways. So we turn to our quadratic formula, which would say opposite of b, in this case that's 3, plus or minus the square root of b squared, negative 3 squared is 9, minus 4 times a, which is 1, times c, which is 9, all over 2a. 2 times a is 2. Notice what's going to happen. We're going to get 9 minus 4 times 9, which is a negative 27 underneath that square root. So this means that the only zeros of our denominator are complex numbers. That means there's going to be no vertical asymptote. In other words, there's no real number that I can plug in that makes my denominator 0. So there's no vertical asymptotes in this case. And obviously, if there's no vertical asymptotes, we can't approach them from the left or the right-hand side. So we can ignore approaching from the left or the right. Let's take a look at the horizontal asymptotes or the horizontal asymptote. Again, the behavior of the graph is always going to be determined as x goes to infinity or x goes to negative infinity. This doesn't work when x goes to any other real number. But if x goes to infinity or x goes to negative infinity, then I can think of this graph as the fastest growth on the top versus the fastest type of growth on the bottom. The leading term on the top divided by the leading term on the bottom. In this case, that's x over x squared, which is the same thing as 1 over x. Now, 1 over x, as x gets really, really, really big, this is like 1 over 1,000, 1 over 1,000,000, 1 over 1,000,000,000, 1 over 1,000,000,000,000. This is 1 over really, really, really big numbers. And that means that fraction is getting closer and closer to 0. The same thing is true if we approach in negative infinity. So if x approaches negative infinity, then the function value is going to give me the same fraction, but I get 1 over negative 1,000,000, 1 over negative 1,000,000,000. And those are all going to be really, really small values, really things that are really, really close to 0. So in both cases, my function value goes to 0, both as x goes to infinity and as x goes to negative infinity. My function value goes to 0. That means my horizontal asymptote is y equals 0, which y equals 0 is the x-axis, so my horizontal asymptote is the x-axis. Let's graph g of x and confirm that we get a horizontal asymptote of y equals 0 and that we have no vertical asymptotes. Again, I've graphed this on Desmos, and so you can see what's happening. In this case, we get this little hump right here around where x is equal to close to 2. And then it kind of tails out on both sides. So this rational function looks like this. You can see both on the left and on the right, we're approaching the x-axis. That's the line y equals 0. So we have a horizontal asymptote there. But there's no place that it shoots off to positive infinity or shoots down to negative infinity. So there's no vertical asymptote on this. So we have a horizontal asymptote of y equals 0 and no vertical asymptote on this function. Let's take a look at one more example of a rational function. This rational function is h of x. It's equal to the polynomial 2x squared minus 8x minus 42 divided by the polynomial x squared plus 5x plus 6. We're going to determine the vertical and horizontal asymptotes algebraically, and then we'll graph that rational function. If you want to, push pause on the video and you can try this on your own. Let's start looking for the vertical asymptote. I always start out by setting that denominator equal to 0. X squared plus 5x plus 6, set that equal to 0. This one will factor, I believe. Factors of 6 that add up to positive 5 are 2 and 3. So we get x plus 2 times x plus 3 is equal to 0. That means there's 2 zeros of that denominator. One is when x is equal to negative 2. The other is when x is equal to negative 3. Now, before I state that these are vertical asymptotes, I'm going to plug those in to my numerator. If I plug in negative 2 into my numerator, I get 2 times negative 2 squared minus 8 times negative 2 minus 42. That gives me a negative 18. So I'm safe with x equals negative 2. Now let's plug in negative 3 into that numerator. 2 times negative 3 squared minus 8 times negative 3 minus 42. That actually gives me a 0. So when I plug in x equals negative 3, I get a 0. And what that really means is that both the numerator and the denominator have a factor of x plus 3 in them. It turns out, I won't go through the factoring process, but we've already factored the denominator. That's x plus 2 times x plus 3. The numerator is 2 times x plus 3 times x minus 7. So notice what we could have done. This is nearly algebraically equivalent to the following rational function where we have 2 times x minus 7 divided by x plus 2. Okay, so while x equals negative 3 is a 0 in the denominator, it's also a 0 in the numerator, so it is not going to yield a vertical asymptote. So this one still has 1. There are there are rational functions that have multiple vertical asymptotes. This just isn't one of them. So we get one vertical asymptote of x equals negative 2. The x equals negative 3 is not a vertical asymptote because it had a factor in the top and the bottom. And we could cancel those factors out, and we were left with no x plus 3 in the denominator after we canceled those. Again, this isn't exactly the same thing because here we could plug in a value of x equals -3. Here we can't because we get 0 over 0, but it's equivalent for all other numbers. Now the horizontal asymptote is a little bit easier on this one. We just look at fastest growth compared to fastest growth. We compare 2x squared to 1x squared. X squared over x squared cancel out, and we just get a 2. That works if x is going to infinity or if x is going to negative infinity. So as x goes to positive infinity, my function value turns into 2. As x goes to negative infinity, my function value turns into 2. That means I have one horizontal asymptote, which is y is equal to 2. So there we go. This has one vertical asymptote, and it kind of has another, what I'd call a false asymptote here. You think it's x equals -3 is another asymptote, but it turns out it's not. So there we go. One vertical, one horizontal asymptote. Now we can go ahead and graph it and see that we get the right sort of graph. Oh, by the way, I didn't state what happens as x goes to -2 from the right or from the left. You could do that by just plugging in numbers that are slightly bigger than -2, like -1.999, and plugging in numbers that are slightly smaller than -2, like -2.0001, and see if you get a positive or a negative value. It turns out on one side you go to positive infinity, and the other side you go to negative infinity. But let's graph this and make sure we have the right vertical and horizontal asymptote. If you graph this rational function, it kind of looks like a shifted version of 1 over x. Obviously not the exact same thing, but notice that as you go towards -2 on the left-hand side, you're shooting off towards positive infinity. On the right-hand side, you're shooting down towards negative infinity. Again, you could have checked that if you'd like. But x is equal to -2, that's the vertical asymptote. And y is equal to +2 is the horizontal asymptote. And we get that. So we're getting this situation here. Now, one little fun fact here, because x plus 3 was a factor of both the top and the bottom, if we trace this function to -3, oops, I might have to zoom in a little bit. You'll see that there's an undefined point when x is equal to -3. That's because when you plug in -3 into your function, you get a 0 divided by 0, and we don't know how to deal with that. So dividing by 0 is impossible. So 0 divided by 0 is undefined. But you get a little hole instead of an asymptote because x plus 3 was a factor of both the numerator and the denominator. So there's a little hole in the graph that you really can't see unless you trace to that point. But there you go. At -3, we saw we had a hole. Now, for a moment, let's talk about these horizontal asymptotes that we've found in our 4 examples. Notice that in this last example, the degree of the polynomial on top and the degree of the polynomial on bottom matched up. And we ended up with a horizontal asymptote of the real number of 2, which just was my leading coefficient divided by my leading coefficient. When we had the degree on top smaller than the degree on bottom, then we ended up with a horizontal asymptote of y equals 0. The degree on bottom, we had faster growth on the bottom, so our entire rational function was going towards 0. When the degree on top, the degree in the numerator, was higher than the degree in the denominator, well, then my entire function went off to infinity or negative infinity, depending on the side. So when the degree in the numerator was more than the degree in the denominator, we had no horizontal asymptote. And in the very first example, the degree in the numerator matched the degree in the denominator. Notice the leading coefficient of 1 divided by a leading coefficient of 1 would give me 1. So I got a horizontal asymptote of y equals 1. Now, this is going to happen anytime that we have a rational function. Polynomial divided by polynomial. If the degree in the top, if the degree in the numerator is larger than the degree in the denominator, then as x gets bigger, the numerator is going to grow faster than the denominator. And so my function is going to go off to positive infinity or negative infinity, or one side one way, one side the other way. But if the degree on the top is smaller than the degree on the bottom, then the horizontal asymptote is going to be y equals 0 for the reasons we have here. And if the degree on top matches the degree on bottom, then we're going to have a horizontal asymptote of y is equal to some real number, and that real number is going to be determined by leading coefficient divided by leading coefficient. That's what these next slides say in mathematical terms. So if the degree of the numerator is bigger than the degree of the denominator, then we get no horizontal asymptotes. If the degree of the denominator is bigger than the degree of the numerator, then the horizontal will have one horizontal asymptote of y equals 0. And if the degrees are equal, then the horizontal asymptote is going to be y equals a sub n over b sub n, where a sub n is the leading coefficient of the numerator, and b sub n is the leading coefficient of the denominator polynomial. That's going to always happen with rational functions. We can look at the degree and very quickly decide what the horizontal asymptote is doing. If the degrees match up, then we take leading coefficient divided by leading coefficient. If the degree in the numerator is bigger than the degree of the denominator, then my rational function shooting off to positive or negative infinity. If the degree in the denominator is bigger than the degree of the numerator, then we're getting close to 0. So we get a horizontal asymptote of y equals 0 in that case. So horizontal and vertical asymptotes of rational functions are important. Also, x and y intercepts of rational functions are important. As always, if we want to find y-intercepts, we can do so by plugging in 0 for x. If we want to find x-intercepts, we can do so by plugging in 0 for y. Now, I want to point out something about finding x-intercepts. If we plug in 0 for our output, that means 0 is going to have to be equal to f of x divided by g of x. Well, this is 0 when the top function, when the numerator is 0 and the denominator is not. So if we're trying to find the x-intercepts of a rational function, since f of x is just a polynomial function, I'm basically doing the same thing I did in the previous section, and that is finding the zeros of a polynomial function. Let's look at example 5 and find the x and y intercepts of this rational function. Now, this example 5 is our first example that we dealt with in this video. So it is the old example 1. But now we'll find the x and y intercepts of this algebraically. I'll start by plugging in x equals 0 to find the y-intercept. Remember, this is a function, so we can only have at most one y-intercept. So plug in 0 in for my x value. I'm going to get the fraction 0 plus 6 divided by 0 minus 2. And that, when I calculate it, becomes a negative 3. So my y-intercept for this function is the point 0, negative 3. For my x-intercept, or maybe I'll have multiple x-intercepts in some case, I'll plug in a 0 for my y value. And just like I was saying before, x plus 6 over x minus 2 being a 0 means that the numerator has to be 0 and the denominator can't be 0 at the same time. So 0 is equal to x plus 6. That means the x value has to be equal to negative 6. When I plug in negative 6 in the numerator and the denominator, negative 6 makes the numerator 0, but it does not make the denominator 0. So we're okay. X equals negative 6 yields an x-intercept. So the x-intercept is negative 6, comma, 0. So there we go. This function has one y-intercept and has one x-intercept. Let's look at the graph of that briefly. Here's the graph of that function with asymptotes drawn. You can see the one y-intercept is at 0, negative 3. And you can see that the one x-intercept is at negative 6, 0. So there we go. We have one of each in this case. Notice that this part of the graph never crosses the y-axis or the x-axis. Again, we're not counting the asymptotes. They're not a part of the graph. Just the rational function is. So there we go. We see we have the correct y-intercept and the correct x-intercept. Let's find the x and y intercepts algebraically for our old example 2. So this is example 6, but it's the same rational function we looked at in example 2. I think in example 2 we had 12 plus 3x. Here we have 3x plus 12 in the denominator. It's the same thing. So figure out the x and y intercepts algebraically. If you want to do that on your own, push pause on the video. I will show you how that's done in a couple of seconds. All right, so let's do this. Let's find the y-intercept by plugging in 0 into the x value. F of 0 would be 0 squared minus 3 times 0 plus 7 divided by 3 times 0 plus 12. Obviously, that is 7/12. And so my y-intercept is going to be 0, 7/12. Whoops. As a fraction, 7/12 is about 0.58 and then 3 repeating. So again, always have one y-intercept. There is a situation where we could have 0 y-intercepts. We'll go over that in a little while. But in this case, most of the time we get one y-intercept. To find the x-intercepts, we'll plug in 0 for y. I'm just going to state that if this function is 0, then the numerator has to be 0. So we will set that numerator equal to 0 and then try to solve. Well, I can't factor x squared minus 3x plus 7 over the integers. There's no factors of 7 that add to -3. So I would have to utilize the quadratic formula, opposite of b plus or minus the square root of b squared minus 4 times a times c. That's 4 times 1 times 7, all over 2 times a. Notice what's going to happen here. Well, let me just go through this. 9 minus 28 is a -19, which means I'm getting a complex or an imaginary part to my x value solutions. That forces me to have no real number x value solutions where the output becomes 0. So the only solutions where the output becomes 0 are complex numbers with imaginary parts. And that means there are no x-intercepts in this situation. So for this function, what we have is one y-intercept and no x-intercepts. Let's go back to the graph of this and just confirm that. Here is the graph. Remember, this was the graph that had no horizontal asymptotes. Notice that as this part of the rational graph comes down, it never crosses the x-axis, but then it goes back up. As this part goes up, it never hits the x-axis, but then it goes back down. So we're never hitting the x-axis. So we have no x-intercepts, just like we computed. And we hit the y-axis at this point. That decimal value of 0.58333 is the approximate decimal value of 7/12. So there we go. By the way, remember, this one was the one that had no horizontal asymptote. It did have a vertical asymptote at x equals -4. Let's do another example where we find the x and y intercepts. This is the function g of x that we had earlier in example 3. Again, if you want to try this on your own, push pause on the video, do it on your own. Otherwise, I will do it in just a couple of seconds. All right, g of 0, we plug in 0, we'll get 0 plus 6 on the top, and then 0 squared minus 3 times 0 plus 9 on the bottom. That's just 6/9, which is 2/3. So we have one y-intercept at 0, 2/3. For our x-intercept, we're going to plug in 0 for y, and that means the numerator is going to have to be 0. So when my output value is 0, then x plus 6 has to be 0. So in this case, x would be equal to -6. That's the only situation. So that means I have one x-intercept at the point -6, 0. So in this case, I had one y-intercept and one x-intercept. Let's confirm that by graphing g of x. So here was that graph. We had the hump right here, and you can clearly see that we cross the y-axis at 0, 2/3. And it turns out we cross the x-axis, we're saying we cross the x-axis at -6, 0. If you zoom in, you kind of see what's happening. We actually go from above the x-axis, then we hit at -6, 0, and then we're below the x-axis, but we don't actually decrease forever. We kind of go down a little bit, and then as we move to the left further and further and further, we come back up and we get closer and closer and closer to that x-axis. But we do cross it at this particular point of -6, 0. So there you go. We got exactly what we thought we would. So the graph looks the way we thought it was going to. Let's do example 8, which is finding the x and y intercepts algebraically on our previous example 4. So the function h of x. We're going to find both the x and y intercepts here algebraically. If you want, push pause on the video and try it on your own. Here we go. So to find the y-intercept, we'll plug in a 0 for the x value. It goes pretty quickly because the numerator, when I plug in 0, becomes a -42, and the denominator, when I plug in 0, becomes a +6. So that is -7. Therefore, the y-intercept is 0, -7. We can only have at most one y-intercept on any function. On this function, it's 0, -7. To find the x-intercepts, we'll plug in a y value of 0. So the output value needs to be 0. If the output value is 0, then the numerator has to be equal to 0. And this is a quadratic equation that we can factor and solve. It turns out you can factor out a 2, then you'll be left with x squared minus 4x minus 21. And then that quadratic will factor into x plus 3 times x minus 7. I won't go through all of the steps there. If you want to factor quadratics, obviously you can check out and review some of our older videos, some of the other videos. So there you go. So we get two x values that give us 0. One is the x value of -3, and the other is the x value of a +7. Now you may jump to the conclusion that we have two x-intercepts. It turns out that we don't have two actual x-intercepts because just like when I find the vertical asymptotes, I have to check to see if I get 0 over 0. If I do get 0 over 0, like we do in this case, then I have to factor the numerator, factor the denominator, and cancel out like factors. And notice that x plus 3 is a factor in both the numerator and denominator. But if I'd cancel out x plus 3 in the numerator with x plus 3 in the denominator, then I'm left with this. And we can see that when you plug in a -3, you're not getting a 0 in this simplified expression. So in the same way we had to cancel out like factors when finding vertical asymptotes, we also have to cancel out like factors when finding those x-intercepts. So this x equals -3 is not an actual solution because we have to cancel out like factors. And therefore, I only get one x-intercept, and that is the 0.70. Let's go ahead and graph that original rational function and see that 70 was my only x-intercept. I have graphed it, and clearly this graph does not cross the x-axis at -3, 0. That's because we had like factors that I had to cancel out. But you can see that it does cross the x-axis at the 0.70. So whenever we're dealing with finding x-intercepts or finding vertical asymptotes, I need to check if my numerator and denominator have any common factors. Cancel those things out if they do. So there you go. That's how to find x and y intercepts on these rational functions. Let's do one last example with a new rational function. We're going to find the vertical and horizontal asymptotes of this rational function, and then also find the x and y intercepts algebraically. So we're going to do all of the types of problems that we did algebraically. Here we have r of x. We have a quadratic divided by a quadratic. If you want to try this on your own, push pause on the video and try this on your own. in a couple of seconds. I'll show you how it is done. All right, let's start with the vertical asymptote or vertical asymptotes. You could have multiple. And in this case, what we would do, and in all cases, what we do is set the denominator equal to 0. In this case, when we set the denominator equal to 0, I get a quadratic equal to 0. That means I can solve this quadratic. The straightforward way of solving this particular quadratic is by factoring. Factors of -10 that add up to a +3 are +5 and -2. They multiply to give me -10 and add up to give me a +3. That means I have two solutions here. One is x equals -5. The other is x equals +2. Now, before I say these are vertical asymptotes, I better check and plug in -5 into the numerator. It turns out if you plug in -5 into the numerator, you do not get 0. In fact, you get -18. So -5 is safe. Also, when you plug in 2 into the numerator, you do not get 0. You get a positive number. So we're safe with x equals 2 as well. Therefore, this rational function is going to have two vertical asymptotes, one at x equals -5, and the other is x equals 2. So we have two vertical lines, which are vertical asymptotes. To find a horizontal asymptote, we just look at the lead terms of the top and bottom. Notice that these two have the same degree, so we can state immediately that my horizontal asymptote is y equals lead term divided by lead term, which is 3/1. So I know I'm going to get a horizontal asymptote of y equals 3/1, which is y equals 3. Again, usually what I think when I do that is I say as x gets really, really big, this rational function is going to be dominated by the fastest type of growth on top versus the fastest type of growth on bottom. And when you simplify that, that becomes a 3. So as x gets really, really big, that becomes a 3. Same thing if x gets really, really big in the negative, that becomes a 3. So I have a single horizontal asymptote of y equals 3. By the way, you only ever get one horizontal asymptote on a rational function at most. So that's what's happening. Now let's take a look at finding the y-intercept and the x-intercepts. Again, we're utilizing this rational function to find a y-intercept. I plug in an x value of 0. Usually in polynomials, it's really easy to plug in an x value of 0. In this case, I would get -18 divided by -10, which if we take 18, or excuse me, -18 divided by -10, we get a 1.8, or as a fraction, 9/5. Whichever way we'd like to write that is fine. So my y-intercept is the point 0, 9/5. To find the x-intercept or the x-intercepts, I'll plug in a 0 for y. That means my numerator is going to have to be 0. So 3x squared plus 15x minus 18 is set equal to 0. This one I can factor out a 3. That would leave me x squared plus 5x minus 6 inside of the parentheses, which gives me, when I factor x squared plus 5x minus 6, factors of -6 that add up to a positive 5. It's going to be x plus 6 times x minus 1. 6 times -1 gives me a -6. 6 plus -1 adds to a 5. So I get two x values that give me 0 in the numerator. One is the x value of -6. The other is the x value of 1. Before I state that both of those are going to be x-intercepts, I should check the denominator. Make sure that when you plug in a 1, you don't get 0. And again, in this case, you do not. Make sure that when you plug in a -6, you don't get 0. Again, in this case, you do not. So the -6 and the 1 both work for my x-intercepts. Therefore, I have two x-intercepts, one which is -6, 0, and the other which is 1, 0. So that's a lot of information that we can get algebraically with rational functions. We get x-intercepts, a y-intercept, we got a horizontal asymptote, and in this case, we got two vertical asymptotes. Let's go ahead and graph this rational function and just see that we got things correct. So if you graph this rational function, you see a number of things happening. We have actually three kind of pieces that are broken up. We have this right-hand side piece, and then this middle piece, and then this left-hand side piece. You can see between the right-hand side piece and the middle piece, there's an asymptote of x equals 2, just like we thought there'd be. Between the middle piece and the left-hand side piece, there's a vertical asymptote of x equals -5, just like we said there was going to be. And then if we zoom out a little bit, you'll see that we have a horizontal asymptote of y equals 3. So this is the situation in which we had two vertical asymptotes, one horizontal asymptote. Also, you'll see that this graph crosses the y-axis at the point 0, 1.8, and it crosses the x-axis at 1, 0, and -6, 0. Again, here are two x-intercepts, the only two x-intercepts we have, and then there's my y-intercept. So all of the features of the graph that I thought should work seem to be working. So that's it for this video. This was a long, pretty extensive video on how to find vertical and horizontal asymptotes of rational functions, and then x and y intercepts of rational functions.